Hey guys, welcome back. Thought I'd share with you the results of some analysis that I've recently been doing, trying to understand the sources of pointing error and what I can do to reduce the pointing error and improve my astrophotography efforts. This is my astrophotography setup. It's fairly standard. I've got a German equatorial mount, in this case a C-GEM. The RA axis, for those of you who have these mounts, you understand that the telescopes rotate about the RA axis, which is aligned with the Earth's axis of rotation, in order to compensate for the Earth's motion during long exposure photography. I've got a imaging scope in which I normally use the Canon T2i, which is not shown here, and I've got a guide scope that sits on top of the imaging scope. And it's the job of the guide scope, the guide camera, and the guiding software, in this case PhD2 guiding, to keep the scope pointed at a single point in the sky, the guide star, during an imaging session. And the more successful you are at that, the better your astro photographs will be, your long exposure photographs will be. But it's a system that's imperfect. It's a mechanical system, so it has imperfections. The atmosphere does not always cooperate. In fact, it rarely cooperates. And so as a result, there is pointing error. Now, PhD2 provides real-time measurements of the pointing error, and we see this all the time when we use the software, in terms of arc seconds RMS. Root mean square is what that means. We want this to be as small as possible. But okay, where do we focus our attention? Well, more often than not, we're tweaking little parameters in the guiding algorithm. Maybe we send our mounts out, as I have just recently done, to have them hyper-tuned, or maybe we preemptively strike and fork over a lot of money for a very expensive mount that with fewer mechanical imperfections. But how much of the pointing error is due to mechanical sources, in other words, mount imperfection, and how much of it's due to the atmosphere? Certainly the atmospheric disturbance, seeing we call it, is a significant contributor, as we all know, to astrophotography. But there are mechanical disturbances in the mount. There are motors that are continuously operating. There are gears. Gears have mesh well or not well, depending on the alignment. There are ball bearings. There are various sources of mechanical disturbance that contribute to pointing error. There's the guiding algorithm itself and its and the performance of the mount in response to commands sent by the guiding algorithm to the mount. In other words, it's one thing to have the guiding algorithm know exactly what needs to be done to correct the pointing direction of the mount, but it doesn't do you any good if the mount is sluggish in responding to those commands. So those latter two sources I might just lump in and call mechanical, and then what's left over will be called the atmospheric disturbance, or the atmospheric seeing contribution to the pointing error. But basically the objective here in this analysis that I was doing and that I'm going to share with you today, I wanted to apply what's called frequency domain analysis to the right ascension and declination pointing error data provided or recorded by PhD2 in its guide log that is provided after each, during and after each guiding session, in order to gain some, maybe a little more insight into the various sources of pointing error. This is a typical guide log, and the guide log we'll be looking at for this analysis here. Did this a couple of months ago. A couple of things that jump out at us, a lot of information here, but the pixel scale, which corresponds to the guiding camera pixel scale, which is 1.29 arc seconds per pixel for that scope and that pixel size with the guide camera. There's the exposure duration, which is basically the update time. This is the every 2 seconds roughly, the guiding algorithm was providing input or commands to the mount to compensate for pointing error. You can set this for longer periods of time or shorter periods of time, and in fact in some situations where I've had seemingly poor pointing performance, I've found that reducing the exposure time down to 500 milliseconds or half a second is actually beneficial. And maybe I'll go back and find one of those guiding logs and look at it. But today we're focusing on this particular one, and we'll be looking in particular at the data, the raw distance in right ascension and declination. In this case, raw means those are the pointing error is measured in pixels, and if I take that pointing error and multiply it by the pixel scale number of 1.29 arc seconds per pixel, then I get the pointing error in terms of arc seconds, and that's what I'm doing. And that data is plotted here for the right ascension on the top and the declination axis on the bottom. It basically looks very similar. This is a 5-hour period of what for me is pretty good guiding performance. A cloud passed over about an hour and a half into the imaging session, but it passed, and the system returned to normal. There was a little excursion on the deck axis that the system did recover from. But for all intents and purposes, the data look very similar and consistent. And in fact, if you look at the RMS pointing error as reported by PhD2, I got an RA, or right ascension error, of about 0.7 arc seconds RMS, and a declination error of about 0.75 arc seconds RMS. Typically for me, though, the right ascension error is on the order of maybe 1.5, sometimes 2 times larger than the deck error, and the deck error is maybe a bit better than what it appears to be shown here. So this is a little unusual in the sense that the right ascension and the declination errors are about the same magnitude. Just to fill in, what is this RMS number, root mean square number? Well, basically, if you took that random series of data in this right ascension and just computed a histogram, you would come up with a bell curve that looks quite like a normal distribution, and the RMS number is actually the standard deviation of that statistically varying pointing error in this case. And so the RMS number is the standard deviation. Think of it as that. And we want to get that standard deviation as small as possible, because that implies that we have a bell curve that is very, very tight around the pointing, the target, the guide star, which represents 0 arc seconds of deviation in these plots. So if we could do something with our system and force that bell curve to be less spread out and more confined, then the quality of the photographs taken with the imaging scope would go up significantly, and that's kind of the objective here. All right, but other than that, this is what you might call a time domain analysis. We're looking at how the pointing error varies in time, and well, we've sort of gotten out of the data what we can get, because basically if you take a look at a section where the guiding performance is kind of typical, you'd say, yeah, it kind of looks the same. I don't see anything jumps out at me. They looks very similar, but are they really similar? Well, that's where frequency domain analysis comes in. I'm going to take the right ascension data and the declination data, convert them into the frequency domain, and when we do that, we get these two pictures. Now, the right ascension and declination look completely different. You'll notice that in the right ascension curve, and by the way, the vertical axis here is an unfortunately arcane sounding units of arc seconds squared per hertz. That's a normalization that's consistent with the so-called power spectrum, and the reason we're doing that I'll make clear here in just a second. But basically, if you look at the right ascension axis, you'll see that there's a number of peaks. These peaks are the mechanical fingerprints of the mount. Again, in the right ascension, as opposed to the declination, there's a continuously operating motor, the worm gear. The worm gear is continuously rotating so that the mount rotates about the right ascension axis, again compensating for the rotation of the Earth. But there are ball bearings, there are gear teeth, there's a gear train, there are a number of continuously moving mechanical components within the right ascension motor that are responsible for these mechanical fingerprints. And what we want to understand is, how important are these what are these mechanical fingerprints? What can we tie them to in the mount? Can you open up the mount and point to a particular component and say that component is responsible for that peak? That's our objective here. And more importantly, perhaps, is to identify which, if any, of these peaks is important. Which is one of these peaks more important in terms of the pointing error than another, implying which component within the mount is more important to pointing error than another. Now, on the other side, we have the declination, and there are no mechanical fingerprints. As we noted, the deck motor should do very little work, and the better your polar alignment is, the less work the declination motor should have to do. At the very least, there's no periodicity, if you will, to the declination response, because that motor is not continuously operating. It simply operates on demand as required by the guiding system to keep the star pointed at the guide star. So we're not seeing any mechanical fingerprints in the declination axis, nor should we. So much of our focus here is going to be on the right ascension axis. Now, I mentioned the connection back to the time domain and why we're using the power spectrum. Well, the area under the curve, the power spectrum, the square root of the area, is the arcsecond RMS number, the same number, the standard deviation, that we could compute from the time domain. So if I calculate a standard deviation, say using Excel or some other simple calculation program, I can come up with a standard deviation and in RMS, which is the RMS number that we're talking about, and that's the same number as the square root of the area under the power spectrum. All right, well, it seems like it's a lot easier just to calculate the standard deviation and be done with it. The problem is the standard deviation calculated just with a series of numbers is, well, it's just a number. I can't get much more insight out of that. But as you'll see going forward, we can pull a lot more insight out of this notion that the area, the square root of the area under the curve, is the pointing error. And for example, I could calculate the area under one of these peaks, and that would be the square root of the area under one of these peaks, and that would be the contribution of that particular peak to the pointing error. And now we can start to differentiate which peaks contribute more to the pointing error than other peaks. All right, let's take a look at our again, our frequency domain picture. I don't like talking in terms of frequencies that are in hundreds of hertz or thousands of hertz, so it's actually more beneficial to talk in terms of period. And we'll just rearrange the bottom axis by taking the reciprocal of the frequency, which is the period of the oscillation. Now, there are a number of features of the mount that have characteristic periods. The worm gear, in particular, for the CGEM, has a period of rotation of 478 seconds. There is a second harmonic, which is half that period, or twice the frequency, at 239 seconds. And for those of you familiar with the CGEM, there is the dreaded and feared 8/3 harmonic, which is not an integer harmonic of the fundamental. Instead, it's 2.667. It's a fractional harmonic. The problem with that is when you're recording the periodic error associated with the worm gear and then implementing that measurement of the periodic error as in a compensation, in the compensation that the mount permits, it's called PEC, periodic error compensation. You can't, there's nothing you can do. There's nothing you can do with the 8/3 harmonic, because all compensation all harmonics that you can compensate for have to occur with an integer number of cycles within one worm gear period. And with the 8/3 harmonic, it takes 3 revolutions of the worm gear to get 8 full revolutions of the 8/3 harmonic. And so this is a consequence of the gear ratios selected in the design of the motor, and it's received some amount of discussion on astrophotography boards and such. But this gives us an opportunity. We can certainly identify, we can certainly see the presence of that harmonic. The second harmonic is clearly present. The first harmonic is significantly reduced, but this is because when I recorded this data, I did have and was making use of periodic error correction. So that's why that fundamental period is as low as it is. It's because it's being preemptively reduced by the periodic error compensation in the mount. Now, there are some other peaks in here, very sharp, narrow, so-called narrow band peaks. These come from the various ball bearings in the system. All right, the one rotation of a shaft of radius capital R, as it goes through one rotation, the much smaller ball bearings will go through many more rotations based on the ratio of the radius of the shaft to the radius of the ball bearing. And these will show up as various narrow band peaks because of little defects in the ball bearing will contact the race of the shaft and of the surface of the shaft and produce a little jump that will contribute to the pointing error, and that's what you're seeing here in these little peaks. And if you could take the mount apart and go in and measure the radius of the shaft and radius of the ball bearings, you could find which component, you could associate each component in the mount with each of these peaks in this frequency domain plot. And so now you begin to see how taking the data apart in the frequency domain is giving us much more insight into the mechanical workings of the system than just looking at the time domain data. Certainly there was no hint of all of this structure and all of these features in the time domain data we were looking at. All right. Now let's relate this plot to the pointing error that we've been talking about. I can take a look at the data here and say, you know what, if I squint a little bit, I'll draw this green line. Everything above the green line I'm going to call a mechanical source, all the peaks, and everything below the green line kind of acts like this pedestal, if you will, the starting point for the mechanical imperfections to become visible. But everything below the green line, I'm going to call that seeing. All right, and now think back in terms of the area under the curve, because now we can start to say, well, the area under the curve up to, say, a period of 100 seconds produces this amount of pointing error, and we can start to differentiate between which peaks contribute to pointing error and which peaks don't. And one very useful way of doing this is by plotting a cumulative pointing error as a function of period, which is what's shown here. Now, let's take a look at the total curve, the blue curve, all right, and we'll calculate the area under that curve, take the square root, and that will be the pointing error up to some period that we decide, say 10 seconds or 20 seconds or 100 seconds, all the way out to the total long period, the maximum period of the data. All right. Now, if you do that, what you see, we start at 0 pointing error, nothing's contributing, and then very rapidly we start picking up pointing error as we start moving out on this axis. And we see little jumps that happen as we go along. We'll talk about that in a second. But eventually this curve kind of levels over, bends over, and just becomes more or less flat. In other words, we don't accumulate any more pointing error beyond a certain point here. So once we hit this knee in the curve, there's really no more contribution to the pointing error. Well, now that's the total seeing plus mechanical. What if we just played the same game, but we used the green, what I'm calling the atmospheric line, or the pedestal line, representing the atmospheric contribution? Well, if I follow that green curve and calculate the area just as we did before, this is the curve we get. Once again, we bend over and it becomes essentially flat for periods of oscillation greater than about 20 to 30 seconds. All right. Now the difference between the seeing curve and the total curve, of course, is the mechanical. So this is, you might say, this is what the mount is responsible for. All right. The whatever's going on inside the mount is in fact contributing to pointing error. That's what we're seeing here. The worm gear that we've been talking about, the fundamental, the second harmonic, and the 8/3 harmonic, they all live out here, but they live out here on the flat, more or less, flat portion of the curve, which is kind of interesting. It provides a great deal of insight. What it's saying is, you know what? Most of the pointing error in our system was accumulated before we even took into account the worm gear. And so if you look at this difference, when does this blue line start to deviate from the green line? When does the mechanical contribution start to pick up? Well, if you look at this red line, there's a little divot, a little step here, it's more or less flat, a little step here, and again it's flat, another step here. These steps are associated with each one of these peaks. So it's the bearings, an imperfection in the bearings, or maybe the imperfections in the shaft surface. It's the contact between the bearings and the shaft that are contributing and causing this accumulated mechanical error in the mechanical source of the contribution to the pointing error. But once again, all of the damage, all of the pointing error is basically accumulated for periods of oscillation below 30 seconds. If we take a look, we back up, take a look, what do we learn from this frequency domain analysis of our guide log? Well, as I just said, the seeing conditions are the dominant source of pointing error. In this particular case, which again for me was very good seeing conditions, about 80% of the pointing error is due to, or is attributed to, just atmospheric fluctuations. And I can't do anything about that. Mount quality and hypertuning, as much benefit as they can provide, for me, it's only going to help me recover some of the remaining 20% of the error for my seeing conditions. Now, if I lived in an area like Arizona or on a mountain where seeing conditions were much better, then the mechanical sources would appear to be much more prominent in the total pointing error, and maybe that's a good legitimate argument for spending more money on a mount or going out of the way to have it hypertuned. I'm still glad I set mine out to be hypertuned, don't get me wrong, but I think it's important to recognize that don't expect radical improvements in guiding performance from hypertuning when seeing conditions, if you live in an area like I do, where seeing conditions are the dominant source of the pointing error. So I have to be realistic about what to expect from the hypertune service that I'm getting. PEC training, periodic error correction training associated with the worm gear and auto guiding in combination, both are pretty successful for the long period contributions. I think the worm gear is a non-player for pointing error. We should really focus on the short period stuff, such as the ball bearings and those kind of components in the mechanical components in the mount. And just to hit that point home a little harder, the infamous 8/3 worm gear harmonic that cannot be handled with periodic error correction is being handled, at least to a large degree, by auto guiding. And then whatever's left over, and there's a pretty clear peak that we are seeing in our frequency domain analysis, even so, all right, even with that observable peak, its contribution to the total pointing error is negligible. So let's not worry about that 8/3 harmonic so much. As noted, most of the pointing error is coming from atmospheric sources and mechanical sources, but that have periods less than 30 seconds. And one of the things that I'm a little surprised about is I would think auto guiding, which again is sending commands to the mount, in this case every 2 seconds, it seems like it ought to be doing a little bit better job in the for those sources of oscillation that have periods in the 10 to 30 second range. And maybe this is a consequence of just having an astrophotography setup with a large mass moment of inertia. Maybe the system is just not responsive enough. Well, that's pretty much all I have here. I hope you found this kind of interesting, maybe a little bit different from looking at the guide logs and the data, guiding data in the time domain. I think you'll agree that there's quite a bit of insight that we can get about the mechanical system and its relative role compared to the atmospheric sources of pointing error. And I'll check in with you later.